So I'm going to give 2 talks. So the first is about filaments, and then I'll do some about our spontaneous reconnection events in the end. Right, so here are my collaborators, my grad students who've been working on this. Okay, so my outline, I'm going to go through a little bit of background about blobs, not too much, and our experimental setup, and I'll go about talking about the blob propagation speed that we see in our experiment, and what actually determines the role of the speed. It turns out to be the neutrals in our experiment. And then I'll show you some new experiments on blob. This is very preliminary, so I just have one movie basically. So
is that the technical term, blob?
That's Krasnikov's term. It's really like plasma filaments, maybe more accurate. So it's elongated structure along field lines. Like so Stuart Sweden, he has done this excellent movie from NSTX where he's puffing in a little bit of gas at one toward location, and then they're imaging the visible light with a camera. And here, I think this is the scrape-off layer. I'm not sure what the other line is. But you definitely see these turbulent structures that's peeling off. You know, they look a bit like blobs, so that's why they call them blobs. So these are elongated along the field lines. But you just
is the dash line the separatrix?
I think it's the separatrix, yeah, it's the dash line. It maps down to the X point. Right, so this is Krasnikov's theory for these blobs. I had dinner with Jim last night, so probably we've already done this, but
well, they're not. We didn't call them blobs. They're just
right, it's just filaments. Yeah, so this is basically standard interchange, right? You have a curvature in grad B drift that separates the electrons and ions, and they give you a charge, give you an electric field that equals B drift this blob out. You can also look at this as being driven by the centrifugal force of the electrons, if that's the species that moves the fastest. Okay, so this blob name for them has been sticking around ever since this paper. This is a simulation by Odd-Erik Garcia. I think he's now up in Tromsø, and he starts out with this little round filament, and he imposes a effective gravity on this thing, and then he lets it go, and it rolls into this mushroom-shaped cloud that go across.
It's like a tokamak without a,
yeah, without a confining. Yeah, that's exactly what our experiment is. Yeah. Okay, so yeah, this is our experiment. It's a tokamak that we have rewired normally for reconnection. So in these experiments, we turned off all the in-plane fields. We only had the toroidal 1 divided by R field. And that's generated by these orange coils, 18 of them. Now here you see a microwave guide. So we have a microwave generator somewhere else that goes in the microwave into the waveguides. We inject 2.45 gigahertz into the chamber. So when the magnetic field is 87 millitesla, the microwaves are in resonance, or the electrons are in resonance with the microwaves, and you can create a plasma that way. This is a view from the inside of the experiment. So for reconnection experiments, I use the green coils, but they are turned off now. But still, I can use all the same diagnostics that we use for reconnection. So here you see a Langmuir probe array. So each little cylinder here is a little metal tip. You bias it negatively, you collect ions, and the more you collect, the more of them there are. You can also sweep the bias on these probes, and you can get the IV characteristic, and from that you can deduce the electron temperature. So we have a total of about 1,500 data channels, and we can swap it in between magnetic signals and electrostatic signals. So right now we have like 4 of these Langmuir probe arrays at different cross sections. Okay, so this is a view inside the experiment again, and we can do things pretty quickly here. It was like one afternoon I made this coil and I stuck it in the inner wall of the experiment. And when I pulsed that, I basically increased the magnetic field just in this inner region. And then I can create a localized plasma filament inside that little region there. So I pulse a capacitor bank onto this in a few milliseconds. So you'll get the LC ring in this coil, and just at the right time, I pulse my microwaves, and I can create a plasma filament right there. So this is what it looks like. Create the filament, and you'll see it propagates beautifully across. And even develops this mushroom cloud shape. I believe this is the first time that has been seen directly in an experiment. Right, so if we go back to, this is supposed to be driven by the equal speed drift. So here you see our electrostatic measurements of the potential, and you do see this vertical electric field that drives it across. But once it starts touching the wall, like something else goes on, like it changes character. But so it seems to fit with Garcia's simulation pretty well. One thing in Garcia's simulation was that the blob was supposed to accelerate at all times. But what we find in like a time radius diagram is that if anything, the blob kind of slows down. It doesn't accelerate. So it's more or less moving once this is the time after which where we are forming the blob, and after that time it's kind of moving at constant speed. And it's about 70% of the sound speed. So that was puzzling us, like why does it not accelerate? Yeah, so again in a naive picture, this blob should accelerate. So we map the potential, and you see this nice buildup of vorticity at either sides to give you the vortex shape of it. But again, why is it that it doesn't accelerate?
So just what is the picture that made it accelerate intuitively?
It's the effective gravity of the centrifugal force of the electrons should just make it should be a constant force, so that the speed should go like with v times t, or a times t should be the speed. Okay. So there's some theories where they thought maybe it's the size of the blob that determines their speed. So we can leave on the microwave for a long time or just a short time to make a small blob and a long time to make a big blob. But we found that it doesn't really depend on the size of the blobs. They move pretty much at the same speed within 15% for these two cases. But then we have one shot where we did something wrong with the gas valve, and there was like much more pressure in there than we normally use. And then we realized, oh my God, this blob is actually moving way slower now. And so there's a very strong dependence on the blob speed with the neutral density. So here you see we double the density, and the blob is now moving at about half the speed. And we then made a scan in the neutral pressure, and we basically find that it goes like 1 divided by the pressure. And also when we measure the electric field, the blob speed seen directly from the Langmuir probes and the equal speed drift, eventually we got those to match as well. Okay, so like it has to be the drag from the neutrals, right, that controls the blob speed. So the picture is that you have an ion that hits a neutral, a charge exchange with this neutral. Now the neutral will carry away the momentum that this ion originally had. And now the new ion is sitting still, and it has to catch up with the blob. So it has to fall in a little bit to this electric field that's pointing down, and then eventually it'll catch up the energy in order to go at the equal speed drift. So this is the way that momentum from the plasma is given away to like a neutral wind. I guess there will be a wind of neutrals coming out from here. And this little current that comes from these ions dropping down to catch up with the equal speed drift, I think in ionospheric physics, this is what they call the Peterson current. Okay, so then we just had to redo the vorticity equation. We had to stick in this ion neutral collision term into the momentum balance and use div of j being 0. And actually in our experiment it's toroidally symmetric, so j parallel is 0. So just from div of j perp being 0, you can derive the vorticity equation. And then like you can integrate this by path, and then eventually you can derive a blob velocity that should go like 1 divided by the neutral pressure. And that's in agreement what we saw. The problem was that the speed we predicted from this was still way bigger than the actual observed blob speed. We predicted a speed that was by a factor of 5 bigger than what we saw. So something was still wrong. Yeah, after a long time, like I thought these Langmuir probes, they're so simple, they cannot go wrong, but in fact, it was the problems with Langmuir probes that was causing this discrepancy. So what we eventually did was we just took some halogen light bulbs, break off the glass, so they have a nice little tungsten filament there, build an array of these light bulbs, and so you put current through them and they get hot, and you can get rid of some surface contamination. So in the purple data here, the filaments are left cold. And when you scan the bias one way, you get this curve. When you scan back again, you get another curve. So there's like hysteresis when the filament is cold. And we believe that this is some surface contamination of these probes. But when you make them hot, this hysteresis goes away. So when they are, like we kind of believed early on the data we will get when we go this way, not the other way. So this will give us about 6 EV plasma, but when we actually did it with a hot probe, we believe that data much better, and the IV characteristics look really nice now. So with the hot filament probes, we get just 3 EV. So finally, when we figured this out, it took a year, I believe, before we got onto it. Yeah, so with that value, we were then able to make the theory fit the experiment. There's one free parameter left, like the ion temperature goes into the collision rate, and adjusting TI to 1 EV, which is reasonable, then we got this theoretical curve. It may be that the blob speed is rolling over at the sound speed, but it's not totally clear. Okay, so basically we found that neutrals were really important in our experiment, and typically they're totally ignored. And if you do tokamak, edge, at least for CMOD, the neutrals should be important there. And I believe in Torpex they'll be all important, but I think your paper agree with that. One of your PL, you get this rounded curve.
Could you remind me, I mean, when people model blob propagation from tokamak edges, they, as you say, don't typically keep the neutral value.
Right.
But they do constant speed modeling. What balances the tendency to...
Yeah, I actually get to that in this experiment here.
Okay.
It's the interaction of the blob with the wall. You get parallel currents going in and out of the wall.
Okay.
And that gives you a constant speed as well.
Now, could you go back to a couple of slides to your diagram of the thing flowing out? Yeah. Whoop, no. Next one. Keep going. Your diagram. The diagram you had. Go forward.
Forward now.
Keep going. Yeah, right here. So there's a well-known effect in the ionosphere, in which if you have neutral winds in the ionosphere, and there's plasma up there, and they used to send up these barium clouds. So they inject a bunch of barium, and then they would see this barium produce structures. And the reason it turns out is because when you have a barium cloud like this, and the neutral wind blows this way, you see structuring on the downstream side. And it arises because if the neutrals are dragging on the plasma, then you have a drift of particularly the ions, I think it's the ions, up. And that polarizes the cloud, just like you get from curvature drift.
Yeah.
And so, but you haven't drawn that effect in this picture. Now, the effect that this would have is to reduce the curvature drive of the system. So you see what I mean? So if the ion, your blob is streaming out, so I'm assuming the ions are, the neutrals are at rest. But if your blob is streaming out, then that would be like in the blob frame, the ions coming this way.
Yeah, I think that's exactly what I was saying.
And then you get a drift up and down.
Yeah. Like that's what I call the Peterson current. So the ion Peterson current are down in the direction of the electric field here. And as of course, the electric field is proportional to the speed. And this current is proportional to E. So like E will just keep building up, the velocity will keep building up until this current going down matches the electron current from curvature and gravity drift going up.
So you're taking that into account?
Yeah,
I would-
that's
I
what
would've thought
that's
that
what the
would-
model does. Or
I would have thought that would appear in the drive term, because it should cancel the curvature drift drive term.
Right, so this is a drag term that cancels this term. So you're basically just balancing these two terms in the vorticity.
Okay, so you've got that in there, that's the
Yeah.
Anyhow, this is well known in the
Yeah, I could imagine.
ionosphere community.
Yeah, I could
They've
imagine.
known this, they've done simulations. on this.
So really the way we solved the paper was by doing this mushroom class.
Okay, I didn't quite get it from your picture there, so
Okay.
what you're actually doing.
Okay, so so once the blob and the tokamak get across the last closed flux surface, the field lines actually go down to the wall. And now you have parallel currents. So when you have a polarization of your blob, you will expect to drive a little bit more current out and maybe some current going in from the wall as well. So that will basically change the amount of electric field you have across your blob. So this is the picture by Dipolito and also Krasninikov. They like to model the blob as a little current generator from the curvature and gravity drift. And then you may have resistivity from the top to the bottom of the blob. And that could include this ion drag or the other terms they find important, like acceleration will give you current as well from ion polarization currents. And then they have a resistivity to the wall through the sheet that develops, that Barrett was talking about, between the wall and the plasma. And that has some resistance associated with it. So what we did was to build this limiter. It's basically just printed circuit boards that has copper, or the metal conductor will be facing the plasma. So we have two of those plates. So we cut like the plasma in two. And each of these small plates can be biased, and we can also measure how much plasma current is going to each little square here. And because they're electrically separated, we can put a bias voltage, like we can bias this part positive and this negative, so we can add an electric field as well. So it's like we put in a power supply in the model as well. So we have one knob we can turn on to see if it actually has an effect. These currents go into the wall. Yes, we can apply a vertical field here. Like so here, I have biased the electric field up, and you see there's a little bit more yellow here and a little bit blue here. And now I bias it down, you now see it's a little bit blue here and a little bit more yellow here. So this is the current going in and out of this limiter. So we can actually drive currents in and out on the top and the bottom of the blob. And when we look at the blob speed, we do see a correlation between the blob speed and this vertical electric field. Like this data here, you shouldn't believe. It looks like we're driving currents into the external walls when we apply a positive bias, but when it's negative, everything seems to work out and we get like a linear relationship between the vertical field applied and the blob speed. So I think this may be the first experimental data where it's verified that this limiter actually does influence the speed of the blob. But we haven't done the quantitative analysis to find out if this agrees with the theory or not. Okay, so just my final two slides on blobs. So also in our reconnection geometry, where we energize the internal coils, we get this configuration 8. And in that equilibrium, we also see blobs happening. So like this movie was basically made last week. Up here, we have the raw density of 4 cross sections measured by our Langmuir probes. And in the lower one here, I have subtracted the time average off, so that you just get a high pass filter is applied. And you can see you definitely have a lot of blobs going around here in the edge, and they zoom around because the plasma is positively charged. There's a guide field to give you an equal speed drift around. It's easier to see in the high pass filter. You'll be able to see something spin around and then going out. Like, so this looks very cool, but I'm not quite sure what to do with it. We should be able to map how these structures go along with field lines, and it looks like the different filaments interact strongly with one another. So I expect some nonlinear interaction going on here. Yeah, so I get the feeling I have to express everything in terms of frequencies and k vectors to get some traction. So I'm not quite sure how to do that with this data here.
But is this also driven by the curvature, or are you getting
This is
Kelvin
probably a
Helmholtz?
Kelvin-Helmholtz.
Kelvin-Helmholtz, right?
I
It's
would,
like Kelvin
I would think, yeah. Sometimes you see just a little blob going around here. More clear here, not a one going on the outside. So if you seriously think this is interesting, you'll probably pursue it. If you don't think so, we'll probably just forget about it. So. All right, so that was my first talk. So I don't know if there's any comments. And also Paul Kazak with Jim Drake has worked on this onset. They have a very nice PLL on this. But there's some evidence that this theory of theoretical work has mostly been in 2D. But I believe there's some theoretical work or some experimental observations that suggest that 3D effects are really important. Now here you see the Bastille Day flare event, and the prominence will just come out towards you, and afterwards you see the brightening on the photosphere where the post-flare loop hits the sun. And you can see that kind of propagates about 80 megameters in about 160 seconds. So it looks like reconnection starts here, and then we have like a reconnection wave propagating away about the alpha speed. So it's definitely 3D up there. Okay, so I'll go through, we have a regime where we see bursty reconnection. So I'll talk about the first 2D aspects of this, and then our new experimental observations in 3D, and we think we understand this now as well. So again, this is our geometry where our in-plane conductors make this in-plane magnetic, or our toroidal conductors make this in-plane magnetic field that has an X point here where reconnection can be driven. So this is the plasma discharge. So again, we create a seed plasma with microwave heating, and then we ohmically heat it with the big transformer we have in the middle of the experiment. And that gives us reasonably hot plasmas, about 20 eV. Like it's good for a basic plasma physics experiment. And 10 to the 18 particles per cubic meter. We have a mean free path that's much bigger than the experiment. And again, our guide field is in the order of 50 millitesla. And the in-plane field is about 5 millitesla. So this is the reconnecting electric field and the guide field, so it's about a factor of 10. Okay. So now at this time, this is the total current in this inner layer. I already formed the plasma, and during this time, I've been heating the plasma. So the loop voltage is about 20 volts, and we have kiloamperes of current. So the heating is actually hundreds of kilowatts. Much more efficient than the microwave. Then at this time, I start driving reconnection from the outside. And you can see this current sheet is forming. Over here you have the reconnection rate. It stays low at about 2 volts per meters. Let me play it over. And then suddenly you see the reconnection rate spikes up now as the current in the plasma drops. Should be playing over again. Yeah, so again you see as your reconnection gets going, the current sheet disappears basically. So it's the back EMF of the current sheet disappearing that drives the reconnection rate, which is not too surprising. As we published this a couple of years ago. We also measured the plasma, like in this movie, these 2 panels are the 2 panels from the previous movie of the current density and the reconnection rate, but we also measure the plasma density and the in-plane electric potential. So during the reconnection event, you see the plasma in the center is being ejected, and it's basically being ejected at the alpha speed. And you also see this in-plane potential that builds up very strongly during the event. And the E cross B drift, at least in this toroidal cross-section, is consistent with this outflow of the ions and the electrons. So the E cross B drift, the radial E cross the toroidal B, give you a drift downwards that is about the alpha speed. So again, we see the current building up while there's not much of a reconnection rate, like 4 volts, 2 volts, and then suddenly the current jumps over and the reconnection electric field spikes up, and there's definitely no linear relationship between the current and the reconnection electric field. Okay, so let's move on to the 3D observations we have. So here we have measured the current in two different cross-sections. And you see the current will suddenly drop in one cross-section while keep going a little bit longer in another cross-section. So it's like a 5 millisecond delay, a 5 microsecond delay from one cross-section to the other. That corresponds to a propagation time of about the alpha speed around the machine. And when this current goes down, then again you get a localized inductive electric field. So you get like a reconnection pulse on one side, and a little bit later you get the reconnection pulse on the other side. So here we have measured the magnetic flux function in 5 different cross-sections, and reconnection will now start in this cross-section. So you should be able to tell, if you look really closely, that the field lines will be ahead reconnecting on this side compared to the other side. And the color is the reconnection rate. And again, you can see it propagates to the outside and then turning off in the middle. Yeah, so this is evidence of like pretty strong 3D effects. So just a cartoon illustration of what happening to the flux surfaces. I will start reconnecting on one side and then go around. Yeah, so this is a cartoon, just to give you an idea. It's like zipping around. Yes. This is actual measurement, and this is what's going on. We now measured the flux function in the entire midplane of the experiment. We measured the reconnection electric field. And again, you'll see the reconnection will start, in this case, about 270 degrees, and then propagates around the experiment. And again, this speed is about the alpha speed, which is propagating at maybe a little bit faster, actually. Okay, but now we have broken toroidal symmetry. So you can also have static fields in addition to the inductive fields. So far, I've only shown the inductive fields. So with our static probes, we have also measured now or characterized the electrostatic fields. And those are really strong. And it was kind of surprising to us. We thought that the static fields would cancel the reconnection electric field at the cross-section where reconnection starts. But it's actually totally opposite. On that cross-section, the static field adds to the reconnection electric field. So you get a whopping total field here on this side.
Which direction is this now? This is in the bidirection?
It's in the direction of the current. In the direction of the decreasing current. And then on the opposite side, if you subtract off the part of the electric field balanced by collisions, it actually goes negative on the opposite side. Okay, so that was pretty mind-boggling to us. And we did check that side many times. So then we had some more observations. Again, as in the tokamak, you can define the safety factor, the toroidal winding number divided by the poloidal winding number. So of course, right at the x-line, this winding number is infinite because you never go around poloidally. But as you go away from the x-line, you can go around poloidally. So right here in this region, this is a cut through. And by dialing in the guide field just right, we can get this region where Q is 2. So out here, a field line has to go around twice and it'll bite its own tail. And we can also dial in another guide field and we can make Q equals 3. Those are the only two rational Qs that we really have experimentally. Q equals 1 doesn't work for technical reasons. Okay, so during the crash, when we dial in Q equal 2, we have measured here the in-plane potential in 4 cross-sections. And you see this very strong potential building up, in-plane potential. And the blue, if you follow the field lines, like it maps directly with the field lines. So this is really a Q equal 2 mode that just rotates with the magnetic field. And this is again the cross-section where reconnection starts at 270. So at this cross-section, this potential has the sharpest profile, and you go away, it becomes a little bit more soft. And then on the back side again, it gets a little bit sharper. Okay. And if I dial in Q equals 3, you get a Q equals 3 structure in this potential when you have a reconnection event. So there's very clear correlation between this external mode and the spontaneous events that we observe. Now, why does this potential develop? When you're away from the x-line, you like the plasma to be more or less ideal, such that E dot B is 0. So during the event, this is what E towardle times B towardle looks like. And it's finite in a huge region. So presumably this potential develops to make the region where the total E dot B is finite should reduce that size. So when I calculate E poloidal dot B poloidal from this potential here and add it to the toroidal part, I get something that's much more localized. So at least for the cross-section where reconnection starts, this potential builds up to make the total E dot B region smaller. So actually in the cross-section where reconnection starts, this potential looks exactly like what you have in a 2D simulation. And
wait a minute, so you're saying is E total dot B total finite at the x line where you're having reconnection?
yeah, there you just get whatever value. Like this potential doesn't take anything away from the E5, E5 right at the x line because B is 0. But when you go away, then you more or less cancel all the external electric field. This is exactly the same potential that you have in your code in 2D for the cross-section where reconnection starts.
I'm just trying to understand why you get the structure at that other rational surface.
The structure.
Normally in
Don't take this with a grain of salt.
Huh?
Take this with a grain of salt, like these separator structures. This is not LAPT. You should take a visual filter on this. Like our probes are 7 centimeters apart. Like this structure is maybe due to limited resolution. We only have one shot where you have to measure everything in, and we have finite resolution. But anyway, the structure of the potential agrees with reducing the E dot B region. And we have established a linear correlation between the reconnection electric field and the size of the potential. This is what you would expect from these arguments. Like, it's a little bit scattered, but there appears to be a correlation at least.
But at the x line itself, the field line wraps right back around on itself. Is that
Right. So at the x line, we definitely need something else in the Ohm's law, and we do not know what that is. And it could be your viscosity. Right, so the reconnection rate builds up exponentially in time, and now I'll try to make a model, a very simple model that may be able to explain, or we think explains this exponential growth behavior. So we basically have three equations that tie together the potential, the in-plane potential, the third component of the vector potential, and the current. Like the first is what I just described to you. There's a correlation between the reconnection electric field and the in-plane potential because E dot B away from the region has to be small. Next, we have like this Biot-Savart's law, or says that the magnetic vector potential is related to the parallel current and has a very strong weighting factor, 1 divided by the distance to a given point. So these two we have pretty much taken care of. Now we have to establish the relationship between the parallel currents and the in-plane potential. And the relationship is the div of J has to be 0. So again, let's look at the data. We have, we basically have current going around. Suddenly the current in one half of the cross-section turns off, leaving behind the inductive electric field in one half of the experiment. Like, so how can you get current continuity from this? Div of J has to be 0. We clearly have very strong gradients in the parallel current, so we need gradients in the perp current to balance this. And the obvious candidate for this is ion polarization currents. So there has to be some ion polarization currents that goes like this with the time derivative of the in-plane electric field. So you can imagine having ion polarization currents that drains the parallel current on one side and then source it on the other side. So as reconnection happens, like this is the potential is building up in time. And there's clearly a time derivative of this potential, and this potential will drive ion polarization currents. So then we try to like fit an analytical function to all our data to the best of our ability and calculate the ion polarization currents from this. In particular, we wanted to figure out what was the asymmetric part in the parallel current that these ion polarization currents causes. So now you should imagine having a flux tube We say in this side end, there's no parallel currents. So you have ion polarization currents going into this tube, and you end up with finite parallel currents up here. So you just have to integrate up along the field line the amount of perp current that goes into this tube. So this is the integral you want to perform along field lines. And again, we made a model for the potential structure that rotates with B, and then we integrated up this integral along given field lines. So if you follow this field line here, if you go to the left, you see you reach a blue region. If you go to the right, you reach a red region. If you take a field line that starts 180 degrees around the experiment, if you go to the right, you'll sample blue region instead of red. So this mode breaks the toroidal symmetry. And you can give finite asymmetric parallel currents from this mode. So we integrated that up, and this is the toroidally asymmetric component of the current we get from this mode building up in time. And it looks reasonably close to the experimentally measured. Like, there's definitely more structure here than we probably see in the experiment, but at least the magnitude comes out right. And our model is quite crude. So with that in mind, I think it's a reasonable agreement. Okay, so now we have established a linear relationship between the potential, or the time derivative of it, and the parallel currents. So what we have is three equations now. First we have the Biot-Savart's law that relates the vector potential to the parallel currents. There may be some external drive as well. Then we have that the parallel current goes with the time derivative of the in-plane potential. And we have that the in-plane potential goes with the time derivative of the vector potential, which is the reconnection rate. And in front of this, we have scalar parameters. They're like geometric factors that we can integrate up from the equations and actually get numerical values for. So I can combine these three equations to get one second-order differential equation with one parameter in front, which is the, you have to multiply these guys together. So it turns out here that this parameter is actually bigger than 0, and then you get exponential growth. And what is nice is that the experimental value we get and the theoretical value are really close, like within a few microseconds. So it looks like this crude model, very crude, seems to capture the essential physics of this onset. So we did some experiments before these that were in a strictly 2D geometry. The electrons were not allowed to go around toroidally, so you did not get much current there. And like one important point is that the potential we saw building up in those experiments was identical to this potential here. But the current at this location here is actually controlled the potential on the opposite side, which has the opposite sign. So in this case, you find that as the potential builds up, you get a negative change in the current, whereas in the 2D case, you get a positive change. So it's the symmetry breaking that causes a change in sign in the parallel current you get when the potential builds up. And that changes the sign in front of this equation here. So in the 2D symmetric case, this sign is a plus. And when you put in that plus, that becomes a minus sign here, and now you should get oscillatory solutions. And that's exactly what we saw in those experiments. That you can step up the drive, and then the reconnection rate will settle in after oscillating back and forth a few times. So yeah, my conclusions. So we have seen some powerful burst of 3D reconnection. It starts at one toroidal location and propagates around the experiment. It occurs only for rational values of this Q, like a Tokamak Q. And it's associated with these Q equal 2 modes, and we believe that the symmetry breaking that the Q equal 2 mode or Q equal 3 mode gives is essential to maintain div of J being 0 during the onset. And then we have this very crude model that seems to predict a growth rate that is consistent with the experimentally observed. Yeah, thank you very much. I just show it's like the best example of change.